We've been looking at finding volumes of revolution, and so far you may have noticed that if we revolve around the x-axis, those slices that we've been doing require an integral with respect to x, and if we're going around the y-axis, you require an integral with respect to y. So the question becomes, what do you do if your function is not of the variable that you require? So I want to look at an example of that and how we can generate a volume even when the variable is the opposite of what we need. So say we wanted to find the volume generated in revolving this region I have here about the y-axis. So we'll draw the mirror image over here to get an idea of what we're talking about. And so this is being revolved around the y-axis. If we go to slice it, then our circles are stacked up the y-axis. And so we would want an integral with respect to y. But our curve here is defined as a function of x. Notice right away you have a problem that if you were to slice this, your inner circles would have a radius being determined by that function. And the outer radius is also determined by that function. The only way you could get those would be to invert this function, right? X as a function of y, which this is not invertible, right? It fails the horizontal line test. So it would break into two functions, one that would be the left side, one that would be the right. So we might be able to do that, but we can't always algebraically invert a function. So we want to have a way of just dealing with the function the way it's given. And so we're going to slice it in a different way. We're not going to use cross-sectional slices. So here's the idea. We partition, as always, and think of our little rectangular area being created at some c sub k. But now, instead of that rectangle swinging around this way, it's going to sweep out around. So I'll try and draw the mirror image over here. And so when that rectangle sweeps around, it's going to create a shape like a paint can, right? It's got a little bit of thickness. It's hollow in the middle. We call this thing a cylindrical shell. So what we're interested in is what is that volume created as that rectangle sweeps around. So what is the volume of that cylindrical shell? So let's try and figure that out. Well, there's a right circular cylinder on the outside, and then creating that hole in the middle is another right circular cylinder that's been cut out. So we can think of this as the difference in those two right circular cylinders. So the volume there would be, I'll call that pi r2 squared h for the volume of the big cylinder. That's just the equation for the volume of a right circular cylinder. And then take away pi r1 squared h, the volume of that inner cylinder that's cut out. So what I want to do is express these quantities in terms of what we have here. Well, I'm going to take that c sub k to be right in the center of that subinterval, so that the radius of the bigger cylinder is just c sub k plus half of delta x sub k, and that smaller radius is c sub k minus half that distance. So I'm taking that c sub k to be right in the middle. So the bigger radius would be our c sub k plus delta x sub k over 2. squared. And then the height of both these cylinders is being determined by the function. So how tall are these cylinders? Well, it's whatever this function is at c sub k. And then take away the inner cylinder, which will be exactly the same except for the radius, which is now c sub k. Take away half this distance. So pi c sub k minus delta x sub k over 2 squared, and then times our function at c sub k for the height. All right, so we've expressed our volume in terms of c sub k and the change in x there, but there's a lot we can do with this expression here. Notice, first of all, they both have a pi and an f of c sub k, so let's take that out of there. And notice then what you're going to be left with is this expression squared minus this expression squared. But they're almost the same expression, right? This is a plus b squared, and this is a minus b squared. So when you square this, you'll get a c sub k squared, but then you're going to subtract a c sub k squared, so that's gone. You're going to have this term squared minus that same thing squared, so that's gone. The only thing that you're going to be left with is when you FOIL this, you have a middle term. Right? You'll have c sub k times delta x sub k over 2, twice that, which would just cancel the half. And then you're going to minus a minus, which will then double that again. It's the exact same expression, but with the opposite sign, and it's minus a minus, so it ends up with the same sign. So from those two, we're just left with 2 c sub k delta x sub k. Now, I'm just going to neaten this up a little bit. I'm going to write it as 2 pi c sub k f at c sub k delta x sub k. Now we have something that looks like a Riemann sum, right, or the terms of a Riemann sum. So the idea now is we have this cylindrical shell, but there would be n rectangles, each one of those rectangles getting revolved, creating another paint can. Those paint cans will be different heights, different radii as we move out and up and down with the curve. So the volume here would be approximately the sum as we add up all those cylindrical shells, v sub k, and then becomes exact as we've always done, right? The idea is then always to, once you've got your partition, then you shrink it down, right? Those things will become better and better approximations of that volume as they become skinnier and skinnier in this dimension here. So that's what this is saying. Really, that mathematically is saying make all those little subintervals shrink down to 0. And that we call the definite integral. Now, what are our limits? When you're thinking of limits, think about what you sliced. You sliced this into a bunch of rectangles that then got revolved. You sliced from x equal a to x equal b. And then this is our v sub k. So in the integral, that becomes 2 pi x f of x dx. So this integral here is a different way of getting the volume. It gets us the volume by slicing in a different method, by finding these cylindrical shells as opposed to those cross-sectional slices. In the cross-sectional slices, what we ended up saying was it was the integral of the area of those cross-sectional circles. Well, you can view this as an area as well. It's a different type of area. If we think about it, when that delta x collapses in, what you're going to have is an infinitely thin cylindrical shell, so you'll really just have the wall of a cylinder. Well, what is the area of that side of a cylinder? Well, if that thing collapsed, so there was no thickness, and we just had a cylinder, we could then cut that cylinder and lay it out flat into a rectangle. So imagine you took your paint can, which is now has walls now that are infinitely thin, and you cut it up the seam and rolled that thing out flat. You would have a rectangle. The circumference around ends up being that dimension of your can. Well, circumference of a circle is 2 pi r. And the r is being determined by this x location. So I'll just say 2 pi x. The height of your can is the function f of x. So the area of this rectangle, base times height, is 2 pi x f of x, which is exactly what we have there. So it's a different area. It's not the cross-sectional area, but it is the area of what these shells become as they become skinnier and skinnier and become just the wall of a right circular cylinder. So this is an area still, and you're summing up those areas to get a volume. It's just we've sliced the object in a different way than cross-sectionally. So now we have our bases covered. We went around the y-axis here and we integrated with respect to x. With cross-sectional slices, when you go around the y-axis, you integrate with respect to y. So no matter whether that function is a function of x or a function of y, one of those two techniques will work. So next time we'll look at an example with an actual function there.